Okay, so welcome to 6.1. In 6, we're finding volumes, not areas. So volume, we have a third dimension that we're going to be looking at. And we're going to be using cross sections. So that's kind of what we're looking at. Now, volume we can think of as the area of an object times the height of that. So if we think about the volume as an integral, volume is the integral of an area function times a little dx. That's going to be a little thickness, height, width, whatever you want. It's another dimension onto area. So area two-dimensional, volume three-dimensional, that's what we have. Now, we're going to do this in a couple different ways. We want to calculate the volume. First, we want to sketch a typical cross-section. Like you're going to want to draw a graph. Then we're going to find the formula for the area of a typical cross-section. Then we'll find the bounds of integration or the limits of integration. Then we're going to integrate to find the actual volume. Now, there's two things that we want to look at here, and one's the disk method and one's the washer method. So let me kind of show you what's going on with those. So let's say you have some function y equals sine of x between 0 and pi, and that's going to basically look like that. If we revolve this about the x-axis, do this, well, then that's going to come there, and we're basically going to get like this footballish looking things. So this would classically be a disk that we'd be looking at, because when we sliced it like this would be a little delta x, and if we turn that piece on its side, it would be a total disk, where basically we know what the area of this is. Area is pi r squared, where this is the radius. Well, that radius right there just comes from a height. So that y value or height would translate into that radius right there. Now this varies, and so this right here, if we were going to set this up, we have our bounds of integration. This would be integral from 0 to pi of pi times the radius squared. Well, the radius is a y. Because we're slicing this, we have a delta x we need in terms of x. So an r squared, if r equals y, that we'd have to square that, and we'd have to square that. So this would be the integral of sine squared x dx. And we would have to have our pi there as well. The pi is always going to be pulled out in front. It's a constant, but this right here is area. This is thickness. That other dimension, that's going to give us the total volume. Now, if we want to, there's another method called the washer method. And the washer method would be about like this. Like if we have some function f of x that looks like that, and we have some function g of x that looks like this. And we were going to, so if we were typically doing this last like section, we're going to find that little bit of area there. Well, we're no longer finding areas, we're finding volumes. And what we're going to do is find the volume of this when we revolve it around the x-axis. So what's going to happen is like this object is going to be like a, I don't know, like a ball with like kind of a water cooling tower out of the middle of it, if you will. So that's what the volume of that thing is going to be. Well, it doesn't really change at all. Let's say that this is the x equals a value. Let's say this x equals b. Really, we're going to take the whole area of that ball shape, and then we're going to the volume of the ball, and we're going to subtract off the volume of that cooling tower. So since we're slicing this, we're slicing it like this. That's a little delta x. A typical cross section would look like this. Now that's a washer, and the washer has two pieces. One is going to be the outer radius, which we'll call as big R. The other one's going to be the inner radius, which we'll call little r. Now, little r and big R, two different things. But if we think about this as an integral, that'd be an integral from a to b of, if we wanted to know what the basically the shaded area is here, that would be pi times r squared. We'd have to take out that little interior piece, which is a little pi r squared. And then if we have this as a delta x right there, it'd be a dx. So that's kind of conceptually what's going on here. To set this problem up, we're taking the bounds of integration from x equals a to x equals b. We have our outside function, our top function, which is our f of x. So we'd have a pi times f of x squared. F of x is giving us the height. That right there is our big R. That's corresponding to that R down here, minus pi times the little radius squared. That right there is our little r, which is our g of x. So we have g of x squared, and that would be a dx. So that would be a washer method. So the shell method, nothing's missing. It's a solid disk. The washer method, we're missing a piece out of it, and that's the big difference here. So if we go back and look at this, that's exactly what we're saying here. The disk, and we can revolve things around the x-axis and the y-axis. When we revolve it this way, we're slicing the x's, so we have a dx. When we revolve around the y, we're going to slice it in y's. Same thing with the washer. It's always the outside minus the inside, outside minus the inside, or right minus left when we're talking about y's. So the first one we're going to take a look at here is the base of a solid disk. Let's find the volume. So the base of a solid disk, if we have the base of a solid disk, that's x squared plus y squared is less than or equal to 1. That's going to be a circular disk that's all filled in. We have less than, so it's equals is the boundary, less than is everything on the inside. The cross section is going to be formed by planes perpendicular to the y-axis between -1 and 1 that are isosceles triangles. So they're isosceles triangles with one leg in the disk. So if we think about that, it's just, if this is our y and this is our x, we're going to have cross-sectional planes perpendicular to the y-axis. So basically what we're going to have is we're going to have a little isosceles triangle, and that triangle will be coming out of the screen towards you. But basically that would be its base. That right there is going to be its height. And then as we go out, that base is getting smaller, the height's getting smaller, but you know, that's the general shape of this thing. So a couple things we need to know is we need to know if we're trying to find the volume, volume is area times width. So we need to know what an area of one of these basic triangles is. And the area is 1/2 base times height. Uh-oh. Hold on a second. Baby's freaking out. Okay, so we have our area is 1/2 base times height. Now, I can tell you that right now, this distance, that's going to be an x. So if we take this equation right here, which is the boundary, which is x squared plus y squared equals 1, and we solve this for x, we have x equals 1 minus y squared and the square root of that. Is there we can go get the owl, buddy. Oh, yes. Good boy. but that right there is only giving us one x, so that's this x right there. If we want that whole length, we're going to have to double that up. So really, we can think of the base as being 2x's, which is being 2 times the square root of 1 minus y squared. Okay, hold on a second. Okay, because we have an isosceles triangle, two legs are the same, and really the leg that's in this disc plane is going to be the same as that. So when you think about this, we just figured out that this base is 2x. This height is 2x. So if we went out the area of this is going to be, it's going to be 1/2 base times height, which is 2x times 2x, which the area is going to be 1/2. So it'd be 2x squared. Now, if this is what x is, x squared is really just going to be 2 times 1 minus y squared. So that's what we're getting there. Now, because this is symmetric, our bounds of integration, we don't need to go from -1 to 1 in terms of y. We can just do half of that. So by symmetry, our integral can be twice the area from 1 to 0 of 2 times. Now, this is the area of this object. Before we had the discs and washers, we had to multiply by pi, but that's just this. This is 1 minus y squared dy, which is going to give us 4 integral from 0 to 1 of 1 minus y squared dy. And continuing this out, we're going to have 4 times y, taking the antiderivative of this, minus 1/3 y cubed, a value between 0 and 1. Plug our 1 in, so we have 4 times 1 minus 1/3 times 1/3 minus, the 0 is just going to kill that, so I'm just going to put 0 there. So all told, we have 4 times 1 minus 1/3. 1 minus 1/3 is going to be 8/3. Excuse me, it's going to be 2/3. 4 times our 2/3. When we multiply that by the 4, we're going to get 8/3 units cubed. So that's that problem right there. Now, we're going to do some classic revolution problems. So the next problem we're going to look at is we're going to revolve about the x-axis. We have x plus 2y equals 2. So really, if we solve this for y, we're going to get y equals -1/2 x plus 1. We're going to revolve this around the x-axis. And we're going to look at this basically. Plus 1. We're up right here at 0, 1. It's going down like that because we're going down 1 and over to that point right there is going to be 2, 0. So the region we're looking at is this. We're going to revolve this around the x-axis. So when we revolve that around the x-axis, this piece will end up being down here. And really what this looks like is nothing more than a cone. It's really a cone. So if we take a typical cross section of this, that's a little delta x. If we look at it on its side, it's going to look like this, where we have a radius r. That radius r is really a height. R equals a y value. And y from this right here equals 1, negative 1/2 x plus 1. So that's the radius. Now, really, there's always a thickness. That thickness right there is a little delta x. It came from that thickness right there. So we want to know what the area of that disk is. Well, the area is going to be pi times r squared. So pi times negative 1/2 x plus 1 squared, that's our area. Our volume is going to be pi times negative 1/2 x plus 1 squared delta x. Now in the limits, when we do this, we're going to take the integral from x equals 0 to x equals 2. So 0 to 2 are this little area piece. So when we're doing this, we're going to have our pi. We have a negative 1/2 x plus 1 squared dx. 0 to 2. Pi comes through. Squaring this thing out, we're going to have a 1/4 x squared. That's going to be a negative 1/2 x and another negative 1/2 x, which is just going to give us a negative x. 1 times 1 is plus 1. So we have dx. Take the antiderivative, add 1 to get 3. So we'll have pi times 1/12 x to the cube, x to the third, 1/2 x plus x. And we're going to evaluate this between 0 and 2. I know it's bad form not to plug 0 in, but when I plug the 0 in, it's going to kill all those things. So I'm just going to plug 2 in. So pi times 1/12, 2 cubed minus 1/2 times 2 plus 2. 2 cubed is 8, so we're going to have pi times 8/12. That's a minus 1 plus 2. Oh, we didn't do our squaring of x here. So square that, sorry about that, which would give us 4/2, which would give us negative 2 there, excuse me. That would cross that out. And then really, if we simplify this a little bit, this is going to be 2/3, so we have 2 pi over 3. And that's my mistake from not, from this expansion, not here. We divided by 2, but I forgot to add 1, which would just square that. 0 cancels out, but that's what we're looking at right there. So we're going to revolve. Next thing we're going to do is we're going to revolve y equals e to the negative x between y equals 0, x equals 0, and x equals 1 about the x-axis. So what that's going to give us is this right here. So y equals 0 is going to be this. X equals 0 is this. X equals 1 is here. So 0, 1. Y equals e to the negative x is going to be a decreasing exponential function. So this is our y equals e to the negative x. Now, when we revolve this around this axis right here, this piece is going to come down here, and basically we're going to have like a cone that's missing the top. So if we take the typical cross section here, like slice, that's little delta x. If we turn it on its side, it's a disk with a radius. That r is going to be a height like that right there. So r equals y, and y equals e to the negative x. So that's that. This delta x is going to give us a little bit of thickness. So if you think about the area of that disk, area is going to be pi r squared, pi times e to the negative x squared. Volume will be pi times e. And you can say this is e to the negative 2x. That's using the rules of exponents times the delta x. So that's like a typical volume that we would put into a Riemann sum. Now, in the limit, we're taking this integral from 0 to 1, it's going to be our area, or really our volume, but that delta x turns into a dx. So we have pi, which we'll put on the outside, e to the negative 2x, so that was our radius squared, dx. Now, I'm not going to do u substitution here, but the derivative of e is e to that thing times that thing. Because of the chain rule, we'd have to multiply by a negative 2. When we're doing the antiderivative, we're going to divide by negative 2. So we're going to have negative pi over 2, e to the negative 2x, evaluated between 0 and 1. Plug these in. Negative pi over 2, e to the negative 2 times 1, minus e to the negative 2 times 0. Nothing more than negative pi over 2. Now, this is going to be just e to the negative, oop, that got weird, e to the negative 2. This is e to the 0, which is 1 minus 1, that's totally a fine answer. I hate the negative on the outside. When I distribute that on the inside, I'm going to get pi over 2, 1 minus e to the negative 2. That right there. My math hub's going to love you for that one. So a couple more examples that we're going to do this. We're going to revolve a function around the y-axis. So if we have x equals 2 over the square root of y plus 1, x equals 0, y equals 0, and y equals 3. And we're going to revolve about y-axis. This right here is a function that looks about like this. X equals 0 is going to be this. Y equals 0 is going to be this. Y equals 3 is going to be this. So this is the piece of area that we're trapping. Now, when we revolve this around the y-axis, we're spinning it this way. So now that piece comes over there. So really what we have is, like, once again, a cone type shape with the top missing. So if we take a typical cross section of this, that's a little delta y now. If we turn that on its side, a little thickness, that's a little delta y. That is a radius. Well, all of a sudden, that radius is this distance, is an x. So r equals x. Well, x equals 2 over the square root of y plus 1. That's our radius. Our area is pi r squared, so pi times r squared, which would be x squared, would be this squared. So we square this, we have 4 over y plus 1. That's our area. Our volume is that times our little delta x. So we have pi times 4 over y plus 1 delta y. So in the integral, we're always going from lowest value, 0, to highest value, 3. So the integral here, we have the integral of our volume, which is going to be pi. We're going from 0 to 3. In fact, we're going to take the 4 out as well. We're going to have 4 pi, 1 over y plus 1 dy. Now, this 1 over a thing, the antiderivative, that's the natural log of that thing. So this is going to be 4 pi, natural log of the absolute value of y plus 1. And we're going to evaluate between 0 and 3. So our 4 pi, plug in 3, natural log of 3 plus 1, minus natural value of 0 plus 1. Well, the natural 0 plus 1 is 1. The natural log of 1 is 0, so that goes to 0. 3 and 1 is 4, so this is going to be 4 pi natural log of 4 units cubed. So cubic units, we are talking about volume again, but that's basically the setup for that one. Now, the last one we're going to do is this. We're going to do a we're going to take a look at this. We're going to revolve around the y-axis. So we're going to revolve around the y-axis. Our function is x equals tangent y. Now x equals tangent y looks about like this. And we're doing it between there and x equals 1. So this is the piece of, that's the piece of like area we're looking at. When we rotate it around here, this piece is going to come back there. So basically, like, this is like a cylinder with a cone missing out of it, if you can like visualize that. So if we take a typical cross section, like a whoop, that's a little delta y. We have a big R and we have a little r. Well, the big R is this distance right there. Well, that distance doesn't change. So our big R here, R equals 1. Our little r is an x. So little r equals x. But because we have a delta y, x equals tangent of y. So we're looking at that right there. So this is kind of our setup. Now if we have our big R, that's our radius. Our area is going to be pi times 1 squared. And our volume would be pi times 1 squared delta y. Because we have a little thickness here, which is a little delta y. Here, if this is our radius, our area is pi times tangent squared y, and our volume is going to be pi times tangent squared y delta y. So basically, if we found the volume of the cylinder and removed the volume of the sorry piece or that cone that's in there, that would give us that volume here. Now, the only thing that's a little bit weird is this. Because we're doing this in terms of y, we need to know what's going on here. So that's where y is going to equal 0. So to find this value, tangent of 0 is going to be 0, so that in fact is 0. So our bound of integration here is 0. To find this y value, we know it's where x equals 1, so if 1 equals tangent of y, to solve this, we'd have to say y equals tangent inverse of 1, which you're going to find out is pi over 4. So we have pi over 4 right there. So setting this up, we have our outside radius, our big R, which is a pi times 1, or just pi times 1 squared dy, minus the outside piece, which is a pi times tangent squared y dy. Now, I'm going to pull the pi out. 0, pi over 4, pi. 1 squared is 1. Tangent squared is a tangent squared y dy. And then we don't know how to directly integrate tangent, but what I can tell you from a little bit of trig and the Pythagorean theorem is that tangent squared y equals secant squared y minus 1. So when we plug that in, here we have pi, and I go from 0 to pi over 4 of 1 minus secant squared y minus 1 dy, our pi, and over from 0 to pi over 4 remains. This negative distributes to here, making this a 2 minus secant squared y dy. So when we take the antiderivative, we have pi. 2 is going to be just a 2y. Derivative of tangent secant squared because it's minus tangent of y between 0 and pi over 4. Plug in our upper bound, plug in our lower bound. So we plug in our upper bound, we're going to have pi times 2 times pi over 4 minus tangent of pi over 4 minus, next page, we'll just start over again. So we have our pi times our 2 times pi over 4 minus tangent of pi over 4 minus plugging in 0, 2 times 0 minus tangent of 0. Good news, as usual, that 0, that actually goes to 0. Pi is pi. 2 times pi over 4 is pi over 2. And then this right here is 1, so you have minus 1. So that's a totally legitimate answer. Or you could get, I guess, we could say this is pi times pi minus 2 over 2. Or we could distribute that through and say this is pi squared minus 2 pi over 2, or whatever you want. But that's that. Hopefully that made some sense. And yeah, that's finding the volume using revolutions, both using shells, which you're going to do when you don't have a hole in it, or washers, but it's not too bad.